And today my talk is recent progress of quantum communication in China, but I will basically talk about the research and the projects by our group, not the whole China. Actually, there is a lot of groups in China, so probably it's not, the talk is, the talk doesn't match with its title very much. Anyway, and we are from the quantum physics and quantum information division, and Jiang Weipan is the director. We have about 14 faculties and around more than 10 subgroups. I'm one of them, and we are working on code atoms, on semiconductor quantum optics, and free space quantum communication, fiber-based quantum communication, and I'm working on fiber and single photon detection. Okay, so here is the content of the talk. I will first talk about the research in the lab, and then the field test and some practical quantum network, and then the future, the quantum backbone, and the satellite. Okay, so first of all, we know the classical encryption is based on the computational complexity assumption, and the BB84 and ECA91, these two types of the quantum key distribution, together with the one-time pad, can provide the information theoretical security. But this one is based on the theory. This one is a theoretical security. Think about if we want to implement in the lab, in the field test, we need realistic devices. We have Alice. Here I just take the prepare and the mirror protocol as an example. Alice is the sender, Bob the receiver, we have the channel. Generally, what's going on here? Sorry. Weird. Okay, sorry. Okay, generally the channel's security is assured by the security proof. So generally the EU can possess the channel. So generally we didn't, we're just using the standard telecom band fiber or the free space is fine. But for the preparation and the detection, you need to consider about a lot of things. First, we'll talk about the preparing the qubit. You need to consider about your light source. And if you are using the weak coherent state, you attenuate your laser to the single photon level, then you need to worry about the photon number splitting attack. And there is a lot of methods. Decoy state is one of them. It's the most widely used. So, and here I will briefly talk about that. And generally, this problem seems to be closed. And we need to care about the random number generator. The random number generator, as long as you believe the quantum mechanics is non-deterministic, and somehow if you believe in the, I'm sorry, yeah. If you believe in if you believe in the quantum random number generator, anyway, we are using this one from the IDQ, and we believe in this one. So kind of this problem is okay. And for the modulator things, there is because when you are doing the QKD, you need to modulate your single photon source to encode the qubit. So for the modulator, there may be some problems. So this is the detection issue. This is the preparing issue. First of all, the weak coherent state and the decoy state method. Generally, we use the weak coherent state. We attenuate the laser into the single photon level. But since the weak coherent state, they obey the Poisson distribution, and there is a probability to have multi photon in the photon pulse, so that the eavesdropper can measure the photon number using QND, and then he will use a noiseless channel. He uses a noiseless channel. He can split the photon and without disturbing the quantum state to achieve the information. And the solution there, as I just said, there are many solutions. And here we take the decoy state method. It's the most widely used. It's just the basic idea is simple, that the Alice just randomly modulated some pulse, the intensity of some pulse, change the average photon number, and then at this condition, eavesdropper cannot tell which one is decoy state, which one is the signal state, and then cannot he cannot attack within the PNS attack. And here are the series, and there are a lot of experiments on that. And I think the longest distance is achieved by our group. It's about 200 kilometers in 2010. But there is a lot of other research around 300 kilometers, but it's with different protocols. For example, the COW protocol and the DPS protocol. Anyway, because you are doing for the decoy state, because you are trying to modulate the intensity of the photon pulse. Generally, you use the modulator, but think about if you are using the AOM, then you may switch the frequency so that the signal state and the decoy state, the frequency is different. And then the eavesdropper the eavesdropper need not to measure the quantum state. It just measure the frequency, and then eavesdropper will know which one is decoy state, which one is signal state, and then eavesdropper can use the photon number splitting attack. So there will be some. So we see there will be some shared channel. One of the solutions is the passive decoy state method. And there are many passive decoy state methods. Here we are using the correlated photon. Here we are using the passive decoy based correlated photon pairs. Here, think about this is the PDC source, parametric down conversion correlated photon pairs. And one idler photon, one singular photon. And for the idler photon, Alice said, so detect the photon. Because this is the correlated photon pairs. So when Alice detects the photon, let's see the trigger state, Alice know the signal photon, for the signal mode, there must be has a higher probability the signal mode will have a single photon. That's like this statistic distribution. And if Alice didn't detect the photon, then the statistic distribution is like this one. So it's automatically randomly has two statistic distribution. One can be used as signal state, the other one can be used one can be used as signal state, the other one can be used as decoy state. This one is called passive decoy state. And we did the passive decoy state experiment in our group. Here you have a 1550 nanometer laser, EDFA, and then goes through a pipeline waveguide, periodically posed lithium nail-based waveguide to generate, for SHG, generate 780 nanometer pump, and the 780 nanometer pump goes through another pipeline waveguide, generated non-degenerate correlated photon pairs. One is using the idler, the other one is the signal. Because I just mentioned that the static distribution is very important, so we first measure the static distribution, which HBT set up. Since in this research, the laser pulse is about 1 nanometer, and the Coherence of the laser is about 1 nanosecond. I'm sorry. And the coherence time of the correlated photon pair is about 30 or 40 picosecond, so that it in theory should obey the Poisson distribution. And here is the HBT measurement result. You can see the G2 is almost 1, so it's a Poisson distribution. And then with this knowledge, and then we start to do the QKD, the passive decoy QKD. Here is the trigger, here is the signal. Signal go to a Macpherson interferometer to generate the time slot, 2 time slot, and then goes through 2 phase modulator to generate the BB84 state, and goes through here 50 kilometers fiber. Here, as you see, the one drawback of the passive decoy comparing to the active decoy is you are using the coincidence measurement. So for the coincidence measurement, the detection efficiency of your single photon detector is very important. So here we didn't using the commercial INGAS APD. We developed our up-conversion single photon detector. The basic working principle of up-conversion detector is very simple. The wavelength for telecom band fiber is 1550, and the good commercial silicon detector is detection efficiency. It cannot detect the 1550. It can only, the optimal wavelength is about 700, 800. And then basic working principle is you use a nonlinear, you use a nonlinear process called sum frequency generation, and you use a strong pump to pump your signal photon 1550 into 700 or 800, and then detect by the silicon detector. This kind of thing has already been developed for about 10 years. It's the detection efficiency for the whole detector can be 40% or something, but the noise is a lot because the strong pump in the nonlinear process, the strong pump will bring a lot of noise. Like here, for example, here is your signal 1550, And here is the pump, for example, 1064 or 1300. The pump will bring some noise like the parametric down conversion and also the Raman scattering in the 1550 nanometer band, and you cannot distinguish it with the signal. You cannot simply use a filter to filter it out. And so we use a long wave pumping. Here in our experiment, we use a 1950 nanometer laser to pump. If you are using a long wave pump, the parametric down conversion naturally be the long wave length side. And for the Raman scattering, it's the anti-slux photon. It's one time magnitude weaker than the Raman scattering, so that you can get a better signal noise ratio. Also, we use the narrow filtering. This one is the volume bar grating. It has a very high reflection efficiency. Anyway, we get about 30 detection efficiency. The whole system detection efficiency is around 30, and the noise is about 100 that counts. It's a room temperature one. And the paper is published in 2013, yeah. Okay, so here is with the detector, we get the passive decoys result. Here is the formula. You have when the idler photon is not detected, Rn is the secure carry rate. When it's detected, is Rt. And here are the gain for different conditions gains, and here are the error rate for different distance. And here is the result. We can see in our lab, we implement a 50 kilometers passive decoy experiment, and the carry rate is about 100 bits per second. It's enough for the text message, for the real-time text message encoding and decoding. And this paper is published here. Think about, people may ask how long the passive decoy our system can go. I think our system can go to 150 kilometers because there are still some loss in the pipeline waveguide. It's a commercial pipeline waveguide. It's not optimal. And also some loss in the commercial telecom band devices. You can reduce it, and it's possible to go to 150 kilometers with our system. And also the clock rate. Here we use 100 megahertz. For up-conversion detector, it can go to 2 gigahertz. So the secure carry rate can improve further. Okay, anyway, then let's talk about the detection of the qubit. The detection qubit, you still have the problem random number generator, but okay. Again, we trust the quantum random generator. And then the modulator, same problem. But here is a different problem in the single photon detector. And there is a lot of types. Actually, some of the authors are among the audience of the attacks. There are several, yeah. So there are several famous ones, for example, the blending attack, and also the time shifting attack. The basic working principle for this kind of attack is simple. It's just like you Alice send some signal to Bob, and just in the middle, the eavesdropper manipulated the signal. They can change its intensity, they can change the time, and then can manipulate the detector of Bob. And there are a lot of countermeasures, and but this game can be immune to any attacks on detector. It's called Merriman Device Independent QKD. It's invented by the Huai-Kuang group. The basic working principle is Alice and Bob, both of them, they prepared BB84 state and then send it to a public station. In the public station, you do the Bell measurement, and this public station can be controlled by the eavesdropper. But eavesdropper can only know the measurement result of the Bell measurement, but she cannot tell which qubit or which bit Alice and Bob choose. But Alice and Bob can, based on the result, Alice and Bob can tell each other's bit value. So I think MDI-QKD is very interesting. First of all, it is not secure as DI-QKD, as you see, because DI-QKD is, you didn't trust anything. You didn't trust your source, you didn't trust your detector. But for MDI-QKD, you trust your source. But for experimentalist, I think some sense is reasonable, because if you didn't receive any quantum signal, just classical information, and then somehow I think it's reasonable for me. And the good thing for MDI-QKD is you can only use laser with the decoy state method. And in Huai-Kuang paper, it can go to 200 kilometers. I think it is highly secure, and also probably it also has a potential to be practical. That's why we are working on that. And here is our first experiment, and together we have the Wolfgang Tito's group, Wade group from Brazil, and the Huai-Kuang group. working on the experimental realization of MDI-QKD. Here, we use two independent laser sources. This laser is electrical modulated programmable laser, DFB laser. Actually, I get this laser from Quantum Tech, Quantum C-Tech. I mean, you can get a sample outside. You can check it. And this laser, because it's internal modulated, so each pulse, each emission pulse, the phase of the sequential pulse is random, so it's kind of secure against the USD attack. And then we go through the imbalanced Mach-Zehnder interferometer to generate the different time bin. We use time bin encoded. And then we go through the amplitude modulator, phase modulator to generate the decoy state, to generate the QCrypt. And then we go through about 50 kilometers fiber, 25 each, and then two polarizer mixed in the interferometer to do the Bell measurement. And here again, we are using the upconversion detector because MDI-QKD is secure no matter what kind of detector you are using, but the secure Q-rate is highly related to the detector efficiency because it's coincidence measurement again. Also, there is another challenging thing for the MDI-QKD is interference of two independent lasers. There are several things you need to be careful. First of all, the two independent laser spatial mode. This is fine because you are using single mode fiber, so it's automatically fixed. Under the polarization, since we are using the inline polarizer, so this is not a problem. But this one will influence the K-rate because we didn't using any feedback system, any automatically feedback system. So when the polarization fluctuates in the fiber, generally we will stop the experiment and then to realign. So generally about 10 minutes we stop the experiment and then realign for the first experiment. And then the tricky thing is the wavelength and the timing. This is the trade-off of these two things. Think about the wavelengths. If you are using the 5 femtosecond laser, two independent 5 femtosecond laser, it's very easy to make the wavelengths overlap because it has a very broadband spectrum. But for the 5 femtosecond laser, if you are not using some frequency code, you're just using the electrical log. Generally, the timing jitter for the electrical system, for QKD system, is about is around 100 picosecond regime, or several tenths picosecond. But that one is too much for the 5 femtosecond laser. So you cannot using 5 femtosecond laser to do MDI-QKD. And then, can we use some very long laser pulse to do such kind of increment? Doesn't work because long laser pulse, the timing overlap is not the problem, but the wavelength, it jumps a lot. So here we chose somehow, I think just at the border it works. We chose the 2 nanosecond laser pulse width, and in our system the timing jitter can be several tenths picosecond. It's okay for this time span. And then for the wavelengths, the FWHM is about 10 picometer for such a kind of laser, and our laser wavelengths can be adjusted with the temperature. So the precision is about 0.1 picometer. So somehow, this here is the picture of we take from the optical spectrum analyzer. You can see the two color means the two different laser and it overlaps. And yeah. So with this system there is no automatically feedback control. So as I mentioned, per 10 minutes we will stop the experiment, and the clock rate is 1 megahertz. Anyway, here you can see here are some gain and error rate, and here is the final K. And anyway, we did experiment, but the experiment result is not very. I mean, it's a good result, but the K rate is very low. Here is the MDI-QKD K rate. I'm sorry, the y-axis is the K rate, and you can see MDI-QKD is about 0.12 bit per second, and they are almost useless. For the text message, you need about 50 bit per second. For the compressed audio, means the telephone, if you want to do real-time encoding, you need about 1 kilobit per second. And if you want to do video, 1 mega. So then the second experiment of our group is try to increase. First, we should increase the K rate at about 50 kilometer. We think it's a kind of reasonable distance in the city. we should increase the bit rate to about 30 bit per second. It's good for the text message. And we want to go to the 200 kilometers. Also, we want to do the field test. Our result is in the lab. It's not field test. It should be automatically run the system. And here is our 200 kilometer MBI QKD. It's just we just put the paper on. We just put the paper on the website. And I think I should talk. Okay, we have this here. We have a 75 megahertz system. Before it's a 1 megahertz system. Now it's 75. So you increase the clock rate is not only good for the K rate, also good for the distance, because MBI QKD somehow it depends on your data size. And when the speed is quick, then you can somehow get a higher kind of signal noise ratio. And hold on. Okay, here we use superconducting single photon detector, not up conversion. Sorry, because sorry for me. And the automatically controlled feedback system. There are two things I should mention. One is the jitter. Because it's 200 kilometers fiber, there will be some, for example, the fiber fluctuation, the fiber drift. 20 minutes for 200 kilometers, it will drift about 200 picosecond. Think about the 2 nanosecond time duration. This is already a lot. And the solution is here. We somehow follow Professor Wolfgang Tito's group's method. We use Alice, Charlie. Charlie is the central station. Charlie using the triggered, Charlie sent the synchronized laser pulse to Alice and Bob. And these two laser pulse will trigger Alice and Bob's laser. And then Alice and Bob's laser can be synchronized very well. This one can fix the time fluctuation of the system. And also here we use the polarization, as I mentioned. Here we also use PBS, a single photon detector, and also the electrical polarization controller to feedback the polarization, because if you care about the K rate a lot. And we are using the superconducting single photon detector, not from NIST, it's from China, Shanghai CAS Macrosystem Institute. And the detection efficiency can be 50%. And that's what we are using. Here are some, here we use a 2 decoy state system, 1 decoy, 1 vacuum. And we go, anyway, let's see the result. We go to 200 kilometers. Here it is. This is our previous experiment. This is the Huaquang Lowe's group's experiment. Only these two papers provided the K rate. And this is the 50 kilometer. We can see the K rate is about 70, maybe 60 bit per second. It's good for the message, text message. Somehow we are here to go. And then you can see Yanlin Tang, my students, talk in the hot topic session. He will talk about it in the detail. And here is the field test. It's just in the Hefei network, which I will talk later. It's about 25 kilometers, Alice to Charlie. Bob to Charlie is 5 kilometers, and this is another paper. But anyway, it's this here is the field, the broad view of the picture. And we put it here. Here is the 30 kilometers field test. You can see it's 30 kilometers, but the loss is similar to 50 kilometers fiber in the lab, because there are a lot of connector. And here we also put the Tito's research result. They didn't provide the K rate. We calculated for them, but probably I'm wrong. Anyway, it's it's just a field test experiment. And this here is the paper number. Okay, and I will go to the field test and the practical quantum network. Okay. From 2009, we start the field test work by our group. And it's the first experiment is a 3-node quantum telephone network. As I mentioned, if the K rate is bigger than 1 kilobit per second, you can do the telephone, real-time telephone encoding, decoding. And here are three points. They are point-to-point QKD. And this one is published in 2009. And then the 5-node all-pass quantum network. This one is also using a decoy state BB84 scheme, only for this point. For this point, it's 130 kilometer. Here, we didn't use point-to-point. We use the trust relay for only this point. And the trust relay is the basic idea of trust relay is just like Alice and Bob and the trust relay. Alice and the trust relay have the point-to-point link. It gets the secure key, and the relay with Bob has the secure key. The relay will announce the result publicly, and then Alice and Bob will know each other's key. That's the basic idea for this one. And we use this configuration in Beijing. It's a small network. It's a 20 kilometers network, basically for the Xinhua News Agency and just to the financial information exchange. And then we use, it's Hefei, but this one is not built by our group. It's built by the Quantum CTech company. And if you are interested, you can ask their CEO. And this is about the 46 nodes quantum network. All the points, not all the points point-to-point link. We use trust relay inside for this one. And here is a beauty picture. Anyway, we just in this network, we do the MDI QKD test. And here is the quantum K distribution machine, like this one. And Jinan, there is another company, but also based on our technology. The Shandong Institute, SIQST, it's 50 nodes, 28 institutions, 90 users, and over 70 kilometers covering area has been well established. And for this one, it's for the Hefei one, we built it up, it works, and then we stop. So now we are using it just for testing, but this one is always working. When it's built, it's always working. And it tested through since 2013, and for the first 3 months, I'm sorry, it's in Chinese, but you can read the number, right? For the first 3 months, the successful rate is about 98.31%. It's not error rate; it's just the successful rate, communication rate. And for the next 5 months, it's about 99.68%. Somehow, I think it's stable. If you are interested, you can see Yong Zhao, the CEO of the company's talk in the industrial session. Okay, the future, the project we are thinking. I should continue the first speaker in the morning, Professor Lam. I don't know whether he's here or not. Anyway, he think we should have some long-range QKD network, and then people will use it. I agree with him. But of course, I think maybe another reason is there is no quantum computer. If there is a quantum computer, I think everyone will use QKD. Anyway, we will build the network. It's based on the trustable relay. We are setting up the quantum backbone. In the backbone, we will have a full kind of network: Beijing, Jinan, Hefei, and Shanghai. They are connected by the main trunk line. And they have the intercity network. You have seen Hefei and Jinan, we use just the previous network, and we will build new networks in Beijing and Shanghai. And this one, total length is just as people mentioned, 200 kilometers. We should finish, we hope we can finish it at the end of the 2016. And we have 32 trustable relay nodes, 31 fiber links, and it's the customer. The customer may be the China Industrial Commercial Bank and the Xinhua News Agency and other company. For this one, of course, this one is supported by the government. So it's just like if I want to give a kind of example, I think it's just like a highway. You just build up the highway. The government build up a highway, and who will pay the highway? Who will pay the money to the highway? Who will use it? Who will pay it? It's just like when we build it up, the customer will pay it. Let's see. And here I should take the example of the United States, the internet in the United States. At first, people didn't use internet, but when you build it a main trunk line, you will use it. So I think this is also our philosophy. You need to have some highway, and then you can charge people. Otherwise, how could you charge people? That's why we are doing that. And another solution, okay, of course, if you want to go to long distance, you will tell me the optimal solution will be the quantum repeater. But I don't know. But for me, I think quantum repeater is still far away, probably 10 or 20 years. I don't know. because I'm not an expert, but from my feeling, probably it's a bit far away. You can use trustable relay. I mean, as long as you believe as long as you are okay with the security. But if you are not with, if you are not comfortable with the trustable relay idea, you can use the satellite, but it's more expensive. And here is the satellite is good because the effective thickness of the atmosphere is only 5 to 10 kilometers. I mean, from the ground to the low orbit satellite is about the attenuation is similar to on the ground, is about 5 to 10 kilometers. So that there's a lot of works. Not only our group, there's also our Europe colleagues. They did a lot of work, and the American, US colleagues. Here is our group's work. First, in 2005, we did the free space quantum entanglement distribution for 13 kilometers, and teleportation 16 kilometers. It's beyond the effective thickness of the atmosphere. But this one is also okay. The attenuation is okay. But you may argue that actually the loss or the attenuation is not only the channel loss is not only the attenuation, but also the geometrical loss, because you didn't have big enough telescope, so that there is another big loss, and also the alignment there is a loss. So generally, people take about 30 to 40 dB as the single kind of a single pass loss, and here we do 22 is about 100 kilometers. We demonstrated the teleportation. I think somehow it's like the satellite-based communication is possible. And then the 400 kilometers is 2009 is just like a single photon. And then 22 is just like if your satellite is moving or rotating or transporting, and what kind of, can you still get the QKD? This is some result. Okay. And now China has, China has we may build about 5 stations: Beijing, Urumqi, Daohe, Lijiang, and Ali. Each station will have each station will communicate with the telescope. Will communicate with the satellite. And the first project will be the high-rate QKD. We will use the satellite as a trustful relay, as long as you trust your satellite. And second phase, we will do the quantum entanglement distribution. We put the entanglement source on the satellite, and then to do the entanglement distribution. And third phase, we will try the teleportation. But this one is we cannot guarantee. We try finish this one in the end of 2016. Okay, this is our dream. You have the main trunk line in the eastern side of China, probably several, I don't know. And then several stations for the free space, maybe continental, intercontinental. That's the dream. And thanks for your attention. Here are my students and postdocs work on that, also colleagues. Xiongfeng is from Tsinghua University, provide theory. And the two from Stanford provide waveguide for me. This is from the Shanghai microsystem. They provide a detector. And Jianwei is the project leader. And here are the funding support. I'm done.
Okay, let me ask some basic specification of the QKD systems that operating in the metropolitan area network in the Jinan or Hefei. So what is the clock rate and typical key generation rate at a certain typical distance?
Oh, the clock rate is 40 megahertz. 40 megahertz.
40 mega,
yeah.
I see.
And the key rate, I think, is 1 kbit per second. But
I see.
Yeah.
So is it enough for some practical applications?
If you are doing the video, we using some VPN. We amplify that. Using some algorithm, amplify that. So that one is not that secure. Not like but we use the quantum key as the seed and amplify that for the video. But for the telephone, yes, you can do that.
Okay.
It's 1 kbit.
One more question. I'd like to know how to confirm the key is correctly relayed via your trusted node architecture, how do you synchronize the key at the really far distance nodes?
Oh, you are talking about the synchronization of the system?
No, synchronization of the delivered key. You know, there are certain nodes and you relay the QKD keys.
Yeah, I understand.
And finally, at the end, we have to confirm that the key is correctly relayed. Which means we have to apply some Beg-Van-Kata protocol between the final key and the frame should be synchronized. And I want to know how to do it.
Yeah, the basic idea, I think, is just like for this node, when it built with the K with the, when it have the K with the Beijing, and it has the K with this node. For example, if we want to have a communication between Beijing and Jinan, if there are two nodes, of course it's many nodes, but if there are two nodes, first of all, these nodes first establish the K with Beijing, and then it will encode his K together with, LK. This is node 1, this is node 2. Node 1 and node 2 has a K. Node 1 and Beijing has a K. And node 1 will use node 2, will use the K between node 1 and node 2 to encode his K and then send to node 2.
Yeah, of course. So do you apply the some person in the hot?
Yeah. Here we use XOR. It's what.
Okay. Let me look later.
Yeah.
Thank you.
And how many users can use one single quantum node? Or relay node?
You're talking about this one?
Well, actually, I talked about the other one, the more the metropolitan one. So how many quantum systems can connect to one particular node, and how many users could use one node?
For this one, 50 nodes is just like 50. Actually, for example, there are 50 nodes, right? For each node, there is only one quantum system, but one sending, one receiving system. Yeah, only one user for one node. 50 nodes. Yeah.
Can you say more? What is the time scale plan for the satellite, Chinese satellite demonstration? Do you have any public information on that? When is it launched, and what is the plan on that?
You are asking about the timing?
I'm asking about the quantum satellite, which you showed in the last slide. So what is the current time plan? When is it going to happen?
2016. We will launch the satellite in 2016. Yeah. The year after, next year.
Is your satellite a trusted node, or is it?
Well, it depends. If you are doing the entanglement-based QKD, it doesn't matter, right? If it's, we will do entanglement-based QKD and also the BB84. If it's BB84, it's trust relay. Yeah.
So you put the entanglement source on the satellite?
Yeah, entanglement source will be on the satellite. I mean, there are two things. Entanglement source will be on satellite. Also, the decoy state laser diode also on the satellite. We'll do both.